Welcome to this episode of SCIEX Now Learning Hub, Introduction to LCNS series. In this episode, we will talk about what mass resolution is and why it is important for your analysis. For accurate results, it is essential to differentiate two signals in a mass spectrum. Ideally, an ion with a specific m/c value would produce a singular straight line in the detector signal, as all ions hit the detector simultaneously. However, in practice, this is not the case. Ions are detected as peaks with a certain width, complicating the distinction between different m/c values. Two signals are considered as resolved if the height of the valley between two signals of approximately equal height does not exceed 10%. Hence, the more ions interfere, the harder it is to achieve resolution of the peaks. Conversely, the smaller the peak width, the easier it is. It is common practice to use the peak width as a measure of mass resolution. The advantage is that this value is independent of the specific conditions under which the mass spectrum is produced and only relies on the instrument's capability to produce a certain peak width. Mass resolution is therefore defined as m/delta-m, where m represents the mass of a particular ion, as determined at the peak apex, and delta-m the peak width, at 50% of the peak height. This value is also referred to as full width, half maximum. Note that m equals the mass-to-charge ratio in this case. Let's calculate the mass resolution as defined at full width, half maximum, with the help of this example. The apex of a peak is observed at m/c 152.0706. The peak width at 50% peak height is 0.0032 daltons. Mass resolution at full width, half maximum, can be calculated as m/delta-m equals 152.0706 divided by 0.0032. As a result, the calculated mass resolution is 47,500 in this example. In practical terms, a higher mass resolution allows you to detect smaller mass differences between ions. While mass resolution refers to the observation in a mass spectrum and describes the ability to separate two signals, as discussed before, the resolving power indicates the instrument's inherent ability to achieve this observation based on its technical characteristics. However, the terms resolving power and mass resolution are frequently used interchangeably. The triple, quadrupole, and TOF mass analyzers have different resolving powers. This comparison highlights the mass spectra of the same compound as observed in both types of instruments. On the left, the full mass spectrum from a triple quadrupole is displayed. Typically, the peak width in triple quadrupole mass spectrometers ranges from 0.7 to 1 daltons, with modern instruments achieving widths as low as 0.2 daltons. These instruments therefore generally provide a mass resolution of approximately 1,000 to 2,000. On the right, you can see the same compound as it is observed in a time-of-flight instrument. TOF instruments are recognized for their high resolving power. The observed peak width is typically around 0.01 to 0.02 daltons for smaller molecules, achieving mass resolutions of 10,000 to 50,000 at full width at half maximum. Though the resolving power of a mass spectrometer remains consistent across a specific mass range, it has practical implications for molecules with higher masses. In the following comparison of simulated mass spectra, we examine two molecules of differing mass at the same resolution. The molecule on the left displays distinct signals from various isotopes, while the molecule on the right, which contains 10 times more atoms, shows a single broad peak where the isotopes cannot be resolved. At a mass resolution of 30,000, both molecules display their isotopic pattern. As molecular mass increases, the peak width increases due to the rising complexity of isotopes even when mass resolution remains high. At extremely high molecular masses, only a single peak is detectable. In summary, Mass resolution refers to the ability of a mass spectrometer to differentiate between two ions that have closely related m/c ratios. Two peaks are considered resolved if the value between them is less than 10% of their height. Triple quadrupoles typically offer a mass resolution ranging from 1,000 to 2,000, while time-of-flight instruments typically achieve mass resolutions between 10,000 and 50,000. Instruments with high resolving power are able to detect signals next to signals with almost the same m/c ratio. This capability even enables the accurate identification of unknown trace compounds in complex samples. Due to the high resolving power, spectra of large molecules provide rich information. Thank you for watching this episode. To view the full training course, including progress checks and a final quiz to earn a certificate, go to SCIEX.com. Log in today to take advantage of the highly rated training material offered in the SCIEX Now Learning Hub. You can use the links below.